Before we proceed with this script, notice that R is giving us a message that one of the libraries used in this script is not downloaded. Go ahead and install it. In order to make the code run, we will need this package. The first thing that I like to do at the beginning of any script is to make sure that I clean the environment and make sure that I get rid of any datasets loaded in the memory or any other variables. The function rm clears the environment. Right now, I have no previous datasets or variables in the environment, so this function will not produce any changes. Also, make sure that you change your working directory to wherever you save the data. After that, load the dataset food CSV. R has the function LM, short for linear model, in order to estimate a linear regression. The main arguments are the formula and the data. For a dependent variable y and an independent variable x, the formula will be y tilde x. The operator tilde is interpreted as described by. Therefore, the R function for estimating a linear regression model is Lm y tilde x and data, which, used just by itself, does not show any output. It is useful to give the model a name, such as M1, which is short for Model 1, then show the results using summary of M1. Let's look at the output. Notice that R prints the estimated coefficients B1 and B2. The intercept parameter B1 is usually of little importance in practice. We are mostly interested in the slope parameter B2. The estimated value of B2 suggests that the food expenditure for an average family increases by $10.21 when the family income increases by 1 unit, which in this case is $100. Next to the coefficients, R provides the standard errors. The summary regression output also includes the test statistic and the corresponding p-value for a two-tailed test of significance. Finally, at the bottom of the regression summary, R prints the estimated standard error of the error term, and right next to it, the degrees of freedom. It is always a good idea to visually inspect the data in a scatter plot, which can be created using the function plot. The plot obtained is a scatter diagram of food expenditures on income, suggesting that we have a positive relationship between income and food expenditures. The R function AB line adds the regression line to the previously plotted scatter plot. The estimated regression parameters B1 and B2 allow us to predict the expected food expenditure for any given level of the income. All we need to do is to plug the estimated parameter values and the desired income value into an estimated equation y hat is equal to b1 plus b2 times x. R, however, does these calculations for us with its function called predict. Suppose we want to predict food expenditures for various income levels. For example, we want to predict when the income is 2,000, 2,500, and 2,700. The function predict in R requires that the new values of the independent variables are organized under a particular form called a data frame. Even when we only want to predict for one income level, we need the same data frame structure. In R, a set of numbers is held together using the structure C. The following sequence shows this example. We create a data frame called xval that takes values of 20, 25, and 27. We use 20 instead of 2000 because the income is measured in hundreds. Then we use the function predict on the data frame xval, and we save the predictions in a variable called y-hat. We display y-hat in order to obtain the corresponding predictions. In order to obtain the residuals, e-hat in our notation, we use the R function resid or residuals on the model M1. Once we have the residuals saved in this variable e-hat, we can proceed to do a plot of the residuals against the income variable. If you remember from the web lectures, this plot is useful to detect heteroscedasticity. We can obtain the fitted or predicted values y-hat in a similar way using the function fitted. The function hist will produce a histogram of the residuals. In the web lectures, we also talked about how to perform hypothesis testing to test for normality of the errors using a Jark-Berat test. The function Jark-Berat test will perform this test for us. This function is available under the package time series, so we have to load this package first by using the function library. Library loads and attaches add-on packages. Notice the output of the Jark-Berat test. The p-value is 0.9688, which is greater than, say, 5%, meaning that we do not reject the null of normal errors. We also perform the Durbin-Watson test for autocorrelation. We need to load two packages in order for the function dw test to work. The p-value is equal to hold on, it's loading. There we go. The p-value is equal to 0.3064, meaning that we do not reject the null of no autocorrelation. Let us calculate a 95% confidence interval for the coefficient on income in the food expenditure model. R has a special function, conf_int of model, that can calculate confidence intervals, taking as its argument the name of a regression model. The result of applying this function is a confidence interval for the intercept on the first row and a confidence interval for the slope on the second row. The two values provided are the lower and the upper bound of a 95% confidence interval. So a 95% confidence interval for the slope is 5.97 and 14.45, meaning we are 95% confident that for every $100 increase in income, food expenditures is increasing somewhere in between $5.97 and $14.44. R calculates by default a 95% confidence interval. If we want to calculate a confidence interval with a different confidence level, say 90%, we use the same function confint, but we specify a default level of confidence. For example, a 90% confidence interval for the slope is 6.68 and 13.73.